All right, and hello everybody, and welcome. I'm glad you're here. Have fun and enjoy. We're continuing our discussion about the strength of this human mimicking robot hand. This is being rendered right now in Keyshot. And I asked the robot hand if it would stick its finger out and let me balance one of the micro hydraulic cylinders on the finger. So there it is. This is the hydraulic cylinder, and that's the piston rod. There's the piston head. These are the cardanic joints that connect it together. And these hydraulic cylinders for the fingers are located in this location where they allow the finger to have flexion and extension in a highly controlled and dexterity function, and in addition they allow the finger to have abduction and adduction. So if both of these, you can see there's two. If both of these extend or contract at the same time, they will tend to move the finger this way or that way. So that's abduction and adduction. So if they both extend, it pushes the finger away from the midline, and that's abduction. And if they both retract, it pushes the finger towards the midline. That's adduction. And if the upper one holds still and the lower one extends or retracts, then it will give flexion and extension of the finger at the high dexterity ability. The power of flexion and extension are given by these ligaments. And so we've gone all over all of that, and we're really working on the strength discussion. We started at the tip of the finger and we've worked our way all the way back. This is another cardanic type joint, the metacarpal phalangeal joint. Now these cardanic joints have rotation. They have all three axes in them, because if you want to simultaneously have flexion, extension, and abduction, adduction, they have to be able to rotate. But the metacarpal phalangeal joints do not rotate. The human being cannot rotate their finger around their metacarpal phalangeal joints. So these have two axes of motion, not three. And we'll take a look here at what we're looking at. Let's see here. This is Rice Terraces of Mu Cang Chi in Yen Bai, I hope I'm saying that right, Vietnam. And it sort of reminds me of what I'm doing, because we get into these forced discussions and we just wander around and they keep leading us off in all these different directions, and you think you're have a point to make or you're in a particular way, and then everything, if you keep studying it and thinking about it, it drifts off into a variety of different other angles and things that you have to think about and considerations. And in addition, it's kind of pretty. And I think here is me in my tiny little shack, I hope I'm right, trying to convince you about hydraulic cylinders in human mimicking robots. And of course, I always want to try to remember to tell everybody, welcome, and I'm glad you're here. I do have a YouTube channel named Patrick Gray, and I invite you to subscribe. I think you'll enjoy it. I have a website, and there's a menu, and you go to give the robot a hand, and on that web page, that one, I try to put links to all the YouTube videos and just some discussion about the robot. I did ask the mannequins. I know, again, I think there's people who are going to say that this robot hand I'm discussing is not possible, but I think it is possible. And of course, there is mechanical, real parts involved with hydraulic pressurization, and any physically real object could potentially hurt somebody. So if you have a physically real object and you are managing it, my advice is to manage it in a manner that is legally allowed and reasonable and safe. And if you cannot manage it in that fashion, then my advice is do not create it as a physically real item. And so now we will switch over to goodbye to Vietnam. We'll switch over to SketchUp, because SketchUp allows measurement and it just makes it simpler to see things. And we have the hand here that's grasping this metal rod. We've already talked about all of this, and we are working on the strength of the hand to see if the strength can do the thing, the hand itself can do the strength activities we want it to do. So we're going to talk about all these fingers are the same. They're slightly different lengths, but all the parts are the same. So whatever we discuss about one finger, it will be true of all of the fingers. And we pulled out one finger, and then we started splitting it apart. And this is the metacarpal phalangeal joint area. And we're looking at this structure, this sort of cardanic joint that this finger is indexed into. And we're looking at strength, remembering that the yield strength of the 2205 alloy stainless steel is 65,000 pounds per square inch. So this cradle that this finger phalange goes into can move. It can move in this axis, and it can move in, okay, so it can move in this axis to give flexion and extension, and it can move in this axis here to give abduction and adduction. And so this holder, this frame is in this frame, or this holding structure is inside of this frame. So we'll look at this holding structure, and it's the same convention we did before. We can look at this. There's 4 bolts here. These bolts are the 1.2, so they're more like 160 to 180 pounds of tensile strength. They're M1.2 alloy stainless steel. And this plate here is allowing the flexion extension movement. And this plate is compressed against this upper plate. And so I think the way to look at whether it's going to have enough strength is to take the surface area of this part of the plate, which is what is mashed up against that upper plate, and that is 0.0014 square inches, and it may hold 92 pounds of tensile force and 46 pounds of shear force. But there's 2 of these, this one here and that one there, so that brings it back to 92. So this can push up with 92 pounds, which is more than the 50 pounds that we were talking about. And again, there's an M1.2 bolt. That another way to analyze this is that it's trying to push out this little piece of metal right here, and that is not quite as strong. I'm not sure it works that way because you're compressing this metal against that metal. So this whole entire area of compression would have to come loose. Now, when the holding frame is pushing up and pushing down, we do have these I-glide polymer bushings as our bearing surfaces. So we have to look at them, and this pin is inside that bushing, and the pin will always be pushing on 1/2 of the bushing. And the bushing, where there is a bushing material that has 13,000 pounds of acceptable pressure that can be put on it. So this pin can push on this bushing with 89 pounds of force. And this pin, this metal pin, has a surface area of 0.0025 square inches times 65,000 pounds, which means that this pin can hold up 162 pounds of tension, which is 81 pounds of shear. And of course there's 2 of these, so that takes it back to 160, because there's one of these on this side, but there's another one on that side also. one here, and one there. And that takes care of the flexion extension side, and then we will look at the place where this frame is connected to this structure here is bolted to the frame of the hand. We've already talked about that frame. That's this part right here. So in order for this little frame to break loose from that bigger frame, it's going to have to pull out this piece of metal, which is right there. And the red area is 0.0022 square inches. The shear, the 0.0022 times 65,000 gives 143 pounds of tensile strength. The shear strength is half of that, but there's two sides to it, so it comes to 143 pounds. So it would take 143 pounds to pull that out of there, and there's two of them. So we have more than enough strength. And again, this bushing, when it's pushing on this, it's the outside area that's pushing. It's only half of it, and that outside area is 0.0088 square inches times 13,000 pounds for the bushing pressure, and that's 114 pounds. So there's enough strength for this holding structure to hold this frame. And the next thing is that this proximal phalange terminates in this part here, and that part goes into this frame, and that part includes the phalange. The phalange has a surface area of 0.0237 square inches, which is 1,540 pounds of tensile strength, which is 700 pounds of 700 pounds of compressive strength. And this little part that has these pins on it, this surface area right here is 0.0189 square inches, which is 1,228 pounds of tensile strength and 614 pounds of compressive strength. And these little pins have a surface area of 0.0025 square inches, so they can hold 162 pounds of tensile strength, and they can hold 81 pounds of shear, and there's two of them. So this thing can hold 162 pounds of shear. So that's okay. That's less than our 50 pounds. And the final thing to discuss is the hydraulic cylinder itself. And the weak point of the hydraulic cylinder, just because of size, is this piston rod. The surface area of the piston rod is 0.0025 square inches times 65,000 pounds per square inch is 162 pounds of tensile strength and 81 pounds of compressive strength. And the cylinder itself, on this end of it, is 0.015 square inches times 65,000, which is 975 pounds of shear strength and 470 pounds of compressive strength. And the other end of this cylinder is this rod that goes into the cardanic joint, and that's the same size as the other ones at 0.0025 square inches. So it has a tensile strength of 162 pounds, but a compressive strength of 81 pounds. So what we're saying is this phalange can push on this with 81 pounds, it can pull on it with 162 pounds, it can push up and push down with the same amount of force. And the flexion, extension, abduction, adduction, there's two of these. So if the finger is pushing back and forth to try to, if you locked up the valve so the piston couldn't move, then this can push with 82 plus 82, 160 pounds to resist abduction and adduction. And flexion extension is not a big issue because we have these big ligaments here to help with that. All right, and she's telling me that we really are done, so I have to stop. We're going to do a force discussion next to show how these ligaments allow the hand to hold up a 200-pound robot.